Yo, what's up? Day 3, baby. Day 3 of coding till I'm good or whatever, till I get a job or something. It's kind of going to be a quicker video. Got working a little bit, so we're gonna try and do one problem. I was already looking at this problem earlier this morning, so and then we're gonna go look through this roadmap again. Probably look at some trees and stuff. Probably do an easy problem on trees. I have to relook at it again totally because I don't really remember how to do trees and stuff like that. So I'll take a look at that. And then I'll probably show you guys what I did yesterday. So like off camera a little bit. So yeah. Hang on, let me respond to this text. Okay. So I already kind of attempted this problem a little bit. The way I was kind of thinking about it was, so we have two linked lists. Yeah, I got two linked lists. Okay, yeah. Anyway, I got two linked lists, and pretty much what I'm going to do is we're going to traverse the linked list, both of them. It's probably going to be kind of like a slower like solution or whatever, but we're going to traverse both the lists. I'm going to have two variables that are just like an empty string, and then as we traverse over the list, we're going to add the values to the list. And then we're going to reverse the string. Yeah. But then we're going to traverse when we put the node back in, we're going to traverse the string and reverse. Yeah. We're going to loop. Yeah, we're going to use a for loop and traverse it and reverse. Yeah. Okay. Let's get started. Let's make our pointers here. Let's code1, code2, and then create our empty string. So let's do num1, num2. Assign them to our empty strings. Whoops. And then we'll do a while loop here. While L, while code1 is not none. We will append that value, right, and then update the pointer. Code1 is equal to code1.next. I think the way that we append the value would be, how to append val in linked list. Oh wait, num1 plus or equal to code1.val or something there? I don't know. Code1.val? Yeah. But then we want to make this into a string. I think that should work. While code2 is not none. We want to append our code2.val. And our code2 is equal to code2.next. Let's print our num1 and we'll print our num2. Let's take a look at that. Got an R. Code2 is not defined. Whoops. time limit exceeded. Man, my typing sucks. Okay. 243, 564. Okay. Nice. Now we want to append these, so let's do our answer is equal to string, and we'll do int num1 plus string int num2, and that should let's add together, and let's print this answer. Let's see what it gives us. Oh, we got an extra bracket. Valid syntax. What? What the fuck did I do wrong? I have no idea what's wrong. Oh, we don't need this. Let's print the answer. Nice. Okay. We got that. So now for char in and move it backwards. We want to create our new dummy. Right, I think this is how you make a dummy. And we want to make our current equal to res char. Current is equal to current on x. And here we want to append our char. So current dot next is equal to list node char. And we want to return the next, so return res on next. Let's see what. Output 807. What are we doing wrong here? I get confused with making dummies. Oh, jeez. Oh, it's because it's I think it's because it's a string actually in char. Oh, we didn't loop in reverse. Is it reverse here? I think that's how you do it. How does this work? I'm not sure. Been reversed. Right, let's see. It's probably the slowest. This is the slowest solution ever. Okay. How is it? There's a sort of reverse. We assume the two numbers do not contain any leading zero except the number 0 itself. Damn, bro. I actually don't know. Why is this not? Come on, then. I don't know. Why does it print 5898? One. Print 2. How is it fucking this? What the fuck? Oh. I think it's because we're traversing from the front and they want us to traverse from the back. So technically this should be... Technically... Oh, fuck. I cannot... Technically it should be 942 plus 9465. Yeah. That gives us 1,047. 00407. Yeah. Okay. So I think we got to reverse num1 and num2. Reverse 1. I don't know if this is cheating, if this will work, but reverse 1 is equal to... How do I just reverse a string? 1, 2, okay, I'll take that. So is equal to num2. Let's comment this out. That means I don't think we need to do that. Let's print this answer. But bro, what? What is going on here? 249. Oh shit, I'm not adding the reverse numbers. Reversed 1. Reversed 2. Maybe now I have to still do this. Okay, let's see if this works. Yay. See, I kind of cheated. My solution is so bad. Like, everyone else is just using an actual linked list. check out the solutions. You guys kind of doing it a similar way. Yeah. Well, it is what it is. I got this new thing. It's called shout out to the Leetcode v3. Pushes it to GitHub every single time. It's pretty cool. Follow me on GitHub if you, I don't know, if you see the video. But yeah, look, it just uploads all my solutions. I only just started doing it. I tested it on Tucson, but look, it even gives you all the information, everything. It's pretty cool. Jump in here. Did you read me the problem, man? Then you code. Pretty solid. Something cool. Anyway, let's go to our next problem. So we said we were going to learn a little bit about trees today. So let's do invert binary tree. I can't even remember the last time I worked with trees. It's probably my data structures class, but I'm definitely going to need to revisit it. I don't know how it works, but just on invert binary tree. Give the binary tree, invert the tree, and return its root. To be honest, I don't even know where to begin, if I'm being completely honest. I don't even know how it works in Python or anything, so I'm not even going to attempt to solve it. So we're gonna watch a video. The binary tree. We're gonna learn a little bit. We're gonna learn some binary trees today. Oh my gosh. Binary tree Leetcode.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve a pretty easy and popular question: invert binary search tree. So all they tell us to do is invert a binary tree. And what exactly does that mean? So let's say that this is our initial tree. To invert it is basically what you can tell in the output, right? So the root stayed the same, but you can see its two children, which were left child 2, right child 7, were swapped, right? So 7 is now on the other side, 2 has been moved, right? So basically we took these and then we swapped them. And when they say invert the binary tree, it's a recursive definition. So take a look at this subtree, right? You can see since we moved it to this side, that's where it is, right? But notice how even these subtrees are different now, right? 1 was initially on the left and 3 was initially on the right, but now 3 is on the left and 1 is on the right. The exact same thing happened with this tree, right? It was moved over here to the left side, but then its children were also swapped, right? So 9 was moved to the left, 6 to the right. So when they say invert the binary tree, what we're saying is visit every single node in the tree, right? And every time we visit a node, take a look at its two children and swap the positions of the children, right? So in other words, if we're given a tree, look at the root node and take its children and then swap the positions, and then recursively run invert tree on the left subtree and run invert on the right subtree. So it's a recursive definition. So we can solve this problem with recursion. We can do a depth first search, whether it's pre-order or post-order, it doesn't actually matter. A depth first search will allow us to solve this problem recursively. So this problem would probably be a lot more annoying if it were iterative, but luckily we can do it recursively. So we can first check the base case. So if the root is null, then we can return null. We don't have to continue. Otherwise, what we're going to do is swap the children. So we're going to save the left value, root.left, in a temporary variable. Then we're going to replace the root.left value with root.right. And then we're going to replace the root.right value with the left value, which we know is now stored in temp. So after we swap the nodes, all we have to do is now recursively invert the subtrees. So we can invert the left subtree, and then we can invert the right subtree. So by doing self.invert tree, what we're doing is making a recursive call to the function we're inside. And once we have swapped the roots children, once we have inverted the left subtree and inverted the right subtree, we know we're finished, so then we can return the root. So there it is. This problem is relatively short code. It's a very good problem to kind of understand the basics of depth first search and tree problems in general. And it's actually a pretty popular problem. And if you weren't able to solve this on your first try, don't feel too bad. Take a look at this trivia. There was a very good engineer who actually failed this problem in their Google interview, but his career still turned out pretty fine. So I hope this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
All right. What I'm a little confused about is so if not root, return none. It's empty. Our temp is equal to root dot left, which is the left side of the tree, I assume, right? Root dot left is equal to root dot right. Yeah. Root dot right is equal to temp.
Now stored in temp. So after we the right subtree. So by doing self.invert tree, what we're doing is making a recursive call to the function we're inside. And once we have swapped the roots children, once we have
okay. If root is not, wait, is it not right? If it is empty, we just return root. Right? If not root, I think that's the same thing. We'll see. We'll make a temp variable. Temp is equal to root dot left, right? And then root dot left is equal to root dot right. Root dot right. And root dot right is equal to root dot left. And then he's saying we want to self-call self.invert tree root dot left, right? Self.invert tree root dot right. Okay. I think I did something wrong. Invert tree root dot left root dot right. Yeah, that's what I did. Temp is equal to root dot left. Oh shit. Whoops. Little mistake. Nope. Root dot left. Right? Temp is equal to root dot left. Root dot left is equal to root dot right. Root dot right is equal to temp. We swapped them. We called it. I think it could be this now. Oh my god. I think, what am I doing wrong here, bro? What the? I have no idea what I'm doing wrong. Oh, we return none. Dude, oh my gosh. If root is none, return none. that. God. If I get confused with this fucking syntax, dude. Like, bro, what is wrong, bro? Oh my gosh, dude. This is crazy. If not, we return none. What is actually happening here? We got the root. Our output is nothing, but we expect something. Okay, bro. I'm literally gonna ask ChatGPT, bro. Jeez. What is going on here? I have no idea what I'm doing wrong. Bro, ChatGPT says there's nothing wrong. What the fuck? Let's copy a test case. Am I missing like a return? Oh, I'm missing a return, I think. Ah, I'm missing. Oh my god, dude. Oh, I'm trolled. I'm a troll. Okay, let's go back. If root is none, that's the same thing, right? Oh, dude, how did I not see that? Yeah, same thing. Okay. Alright. Cool. Forgot to return. Classic. Nice. Okay. That's cool, man. We're learning a little bit of trees. Learning some trees. Let's try... Same tree. Let's try same tree. Let's see. Maybe it might be a quick solution. I don't know. You can get an extra problem in. I got work soon. Let's take a look. Okay, let's kind of do it the same way. So, if root is none, let's return none, right? We probably want to check if root dot left is equal to root dot right. Root dot right, then we probably want to recall what we just called, right? Oh my gosh, dude. Let's go back. Let's check out our two numbers. Oh, whoops, not this one. The binary tree. I can't even remember how we... Okay. We'll do self dot invert self dot is same tree. Oh shit, it gives us P and Q. Oh shit. I assume P must be the root. Well, I guess if P or Q, if P is none or Q, what are we returning here? Or Q is none. Guess we can just return none. Let's just see what that does first. I'm curious if that passes the test case. No. Okay, we're returning. Let's just... Guess we can just return true. Right? Because they're the same. P. Is that how I refer to it? If P dot left? P dot left is equal to P dot right. We recall the function. After the same tree. Dude, I have no idea. False. Guess we just return false. I don't know. Maybe change this into a while loop. Well, P dot left is equal to P dot right. Can we do a while loop here? I have no idea. If P dot left is not equal, right, return false. What else we can just return true. Jeez. Let's see how many test cases were possible. I'm just curious. 2. Nice. Nice. I think I'm missing something, bro. Oh, I don't want to look at the solution yet. I can do it. I can do it. I believe. I believe. Oh, P dot left does not equal P dot right. Find a way that we can loop.
Hey everyone, welcome back, and let's write some more neat code. Since we already went through most of the base cases, this is going to be, so if the and Q trees, empty trees are technically equal. Now if statement Q, the only thing difference between this and the one above is this one is and, this one is or. So if it executes, that means only one of them is null. Now what happens in the same tree, right? So empty is that thing, right? You can paste this here, so if,
so close. P. What'd they do here? Oh gosh, got so much shit. Did I just get rid of it? Oh my god, dude. Oh no, I didn't. Not P or not Q. True or false.
This is true, or this both values are actually the same. We're gonna call E on to know from
I don't even need
for
a
the
while loop, dude. Oh my gosh, dude. I didn't even know that it just like goes through like that, like the tree. Okay. Just return false.
we can also return false. We don't actually need this third condition. So if this statement does not execute, that means that both of the nodes P and Q are non-empty, right? And the values are actually the same because if this does not execute. So then what are we going to do over here? Now we're going to do the recursive step. We're going to call is same tree on the left and right subtree. So if P, we're going to call it on P left and Q left, and we're going to call it on P right and Q right. And what do we want to know when we're comparing the left tree and the right trees? What do we want to know? We want to know that both of the left subtrees and the right subtrees are equal. So we want this to be true, and we want this to return true as well. So we're going to take these two the return values of these two function calls, and we're going to AND them together. And if the AND is true, we're going to return true. If the AND is false, we're going to end up returning false. And this is the recursive step. This is the only thing that we have to return. This is the entire function. So this is a pretty good problem to practice your tree traversals, your depth first search practicing. So I think it's a
same tree. And resolve the P dot right, Q dot right. If not P and not Q. Let's just make it the same. Actually, no, fuck that, dude. I kind of want to read this syntax a little bit. Oh, we're checking the values. Oh, so this is kind of right. It should just be p dot val, and then p dot q dot val. If one of nodes is empty and other is not. Both are empty. Both are empty. Right. And then we're checking if the vowels are different. And then this is our recursive pool. Let's submit that. I need to go over depth first search a little bit. I haven't looked at that in a long time. Like,
today, I'm going to teach you depth first search. Depth first search, or DFS, is an algorithm for search I want you to visit. Let's perform DFS on the following graph. We want to know all the nodes that are discoverable from the root node A. Along the way, we'll keep track of two things. First, nodes we visited will be colored black. Nodes that are in the stack that are in line to be visited will be colored gray. Starting our algorithm, A is the first node we'll visit. We'll keep track of the stack in the top left corner. We pop A from the stack and mark it visited. We also add its adjacent nodes into the stack. I'm adding the rightmost node first because I think it's easier to follow visually if we go left to right. B is the next node popped from the stack. We mark it as visited. Notice G is the only node in the stack, but as we add B's adjacent nodes, G gets moved to the bottom. C is the next node we'll pop. C and D have no children, so nothing to add to the stack. We reach E and add its child F to the top of the stack. I'll let the rest of the algorithm finish without voiceover. Finally, there is nothing left in the stack, so our algorithm is finished. Here's the code for depth first search. There is a link to a working Python example in the description. The code.
Nice. Okay. Cool. All right. Well, I'll show you guys what I did the other day. Just kind of wanted to change the color around a little bit. So yeah, I added this video before. It was up here. Move this down a little bit. And I just kind of changed the background colors, just messed with the CSS, made the buttons orange. Just kind of made the feel of it a little orange. Orange is my favorite color, so yeah, just making it orange. What I do need to do is I need to change these from black to white. Just have to redesign them though. Yeah, I'm planning on adding a little JavaScript function to switch the coloring. Kind of working on that right now. I have the little outline of the button and everything. I just need to apply all the CSS to it to actually switch, make the functionality of it and stuff like that. But yeah, I mean, that's probably the next goal. I'll do this button. We gotta kind of figure out the coloring and everything, but yeah, probably do that. I kind of want to add a little bit of a back end to it. Maybe add a little blog page or something. That's kind of in the future what I want to do. Just add like a blog, or maybe, you know, there's some posts or something and a little bit of a back end, just to kind of show off my back end skills. I've got no idea though. Kind of, I've never really worked with a database or back end. I've done classes and stuff, but I don't really count that really any experience or anything. But that's probably the goal eventually. Let me know though if anyone really watches this, if you know, maybe there's something else I can add. You know, I kind of want to get rid of this area or add something here. It's like half the page is gone, so maybe I can add some like projects or something here that I'm doing or something. But yeah. Anyway, I have work in like 20 minutes, so I'll probably see you guys later, man. See you guys tomorrow.